1957. A new era beckons as the USA and Soviet Union engage in a race to space, later followed by France. 4 years later, the French space agency Cnes is born. Its Toulouse Space Center opens in 1968. Earth observation from space rapidly becomes a priority. 1970. The USA begins testing orbital radar technologies. In 1978, they launch CSAT, the first ocean-observing satellite, and in 1985, GeoSat. In Toulouse, space-based location and data collection systems are successfully developed. Éole and Argos, and work on geodesy and precise positioning paved the way for the first joint French-US projects. From the outset, Toulouse establishes itself as a pivotal player in the oceanography revolution, with the decision to develop the Poseidon radar altimeter at the start of the 1980s. Pioneering visionary engineers pull out all the stops in their quest to measure sea surface height to within 2 centimeters all over the globe. And in 1987, the USA and France agree to develop the Topex Poseidon satellite, successfully launched in 1992. A new global picture of the oceans begins to emerge. Sea surface height, ocean circulation, the El Niño episodes observed in 1994 and forecast in 1997. Oceanographers realized it would be impossible to observe the oceans precisely without satellite data. As a result, satellites soon become key assets in understanding ocean circulation and its variations. Meanwhile, the international community is waking up to the reality of climate change and the central role the oceans play in climate variations. The Rio Earth Summit enshrines the first major declarations in support of sustainable development. 20 years later, in Copenhagen and then the Rio+20 summit, the obstacles to consensus are plain for all to see. But over these past 20 years, sustained development of space assets and the continued efforts of scientists working together have achieved the transition to operational oceanography. JASON 1 in 2001, JASON 2 in 2008, JASON 3 in 2016. Around this family of satellites built up by Cnes and NASA, now partnered by EUMETSAT and NOAA, other missions emerge, like the French-Indian SARAL satellite in 2013. At the same time, the European Space Agency's ERS Envisat satellites paved the way for the Copernicus program. A scientific community takes shape, spearheaded by Toulouse, where more than 1,000 space oceanography research scientists, engineers and technicians are working in fundamental and applied research, instrument design and fabrication, and data processing. Satellite altimetry provides vital data for the oceanography research and operational oceanography community. The data collected over the last 25 years show that sea level has risen, with large regional variations of the order of plus or minus 10 centimeters. Meanwhile, the global mean sea level has risen by 3 millimeters a year, a total of 8 centimeters over the same period. The question now is, how will it evolve in the decades ahead as the effects of global warming kick in? Satellite monitoring has brought new insights into the variations of ocean circulation and the major ocean currents. For example, the Gulf Stream could be impacted by global warming, resulting in cooler weather across Europe. Daily detection of sea level anomalies lets us forecast the onset of large-scale ocean phenomena like El Niño and La Niña, and the calamitous climate effects they leave in their wake. Altimetry is of great value in geodesy and geophysics for observing the figure of the Earth. particularly to measure the marine geoid and bathymetry. It is also useful for determining the topography of a glacier or the thickness and characteristics of ice, including sea ice. A new and promising science spawned by satellite altimetry is space hydrology. This discipline monitors the level of lakes, closed seas and major rivers, with the ultimate goal of improving how we manage water resources. Observing and understanding is one thing, but predicting is another. Ocean models have been developed that use observation data to predict ocean variations. By coupling these predictive models with atmosphere models, we can not only generate weekly or seasonal weather forecasts, but also conduct in-depth climate change analysis. Similar developments are underway in the field of land surface hydrology. The value of the program developed by Cnes and NASA lies in how it has enhanced climate change research, while at the same time nurturing practical model-based applications to underpin more sustainable stewardship of the oceans. Applications like optimizing shipping routes to take advantage of currents, enhancing marine weather forecasting by predicting wave and swell heights, supporting response efforts in the event of an oil spill, helping to identify polluters flushing their ship's oil tanks at sea, better apprehending the risks of installing and operating offshore oil rigs, and helping to manage fish stocks more sustainably. Many other applications are also emerging, notably to support planning decisions and operations in coastal areas. Operational oceanography is the result of the vision and foresight of space agencies and research teams. This brand new field covers the full gamut of seafaring aspects and is set to really take off in the coming years, extending its spectrum of commercial, public service and sustainable development applications. Set in train by space agencies, operational oceanography is a vital tool for both societal and research applications. Demand from the scientific community for data processing and forecasting is strong. In this respect, it could be said that research is a regular customer of operational oceanography, and this sustained research effort is one of the keys to satellite altimetry's huge success. Today, teams based in Toulouse are playing a key role in Europe's Copernicus program with the Sentinel-3 satellites and the future Sentinel-6 JASON-CS satellite. They are also working with their US counterparts to develop the SWOT program that is set to take the science of fine-scale oceanography and hydrology to a new level. SWOT's instrument will provide a two-dimensional picture with 10 times more resolution and accuracy, and the ability to cover the entire globe every 21 days. SWOT will be the first satellite dedicated to studying land surface waters. It is expected to measure the area, height and changes in volume in more than 20 million lakes, as well as the discharge of rivers more than 100 meters wide, offering a vital tool to manage an increasingly scarce resource. Oceanographers will also for the first time be able to delve deeper into mesoscale phenomena like ocean eddies spanning 10 to 100 kilometers. Such small eddies alter currents and play a key role transporting heat, carbon dioxide and nutrients from the upper to the deep ocean. Observing these processes on a global scale is essential for studying climate. What will observing internal tides tell us about ocean circulation? And what about coastal oceanography? Finer resolution will give us new insights into erosion and inform land planning decisions impacting coastal regions, where 70% of the world's population lives. Planned for launch in 2021, SWOT is the big challenge for the years ahead. Teams in Toulouse and the US are devoting all their energy and expertise to the project in support of the sustainable stewardship of our planet.